Welcome back. ASP Isotopes Inc. trades on the NASDAQ under the symbol ASPI and is a pre-commercial stage advanced materials company dedicated to the development of technology and processes to produce isotopes for use in multiple industries. We're happy to welcome back the CEO, Paul Mann. Nice to see you, Paul.
Good to see you again. Thanks for having me and for inviting me to present. So I'll go through the slide deck in about 15, 20 minutes or so, and then we can go into Q&A. So we're NASDAQ-looking companies, so usual kind of forward-looking disclaimers. Please take a look at our Form 10-K for risk disclosures and what have you. So we're a company that operates in three industries: the medical industry, the semiconductor industry, and the nuclear energy industry. And we do that via three verticals in the company. ASP Isotopes in the middle produces stable isotopes, and we've just finishing the construction of three plants here in South Africa that should start producing product between now and the end of the year. And then we have PET Labs, which makes isotopes for the medical industry, and that's already generating free cash flow. It supplies all the radioisotopes to sub-Saharan Africa. And then Quantum Leap Energy is a division we started about a year ago. That's going to focus on nuclear fuels for the future, specifically high-assay, low-enriched uranium. And these are milestones for 2024. We've achieved most of those already. And hopefully we'll put out some milestones 2025 shortly. And so look at us, what is an isotope? And it's basically a very special chemical. When you think about carbon, oxygen, and silicon and nitrogen, they're different elements. They have different numbers of protons inside the nucleus. They have very different chemical properties. Some of them are solids, some of them are gases. And you can separate them very easily because they're chemically different. They react differently. Isotopes are basically the same version of the element, but have different numbers of neutrons inside the nucleus. And that gives them different physical properties, but they're very hard to separate chemically. So take, for example, silicon. Silicon is found on the beach, silicon dioxide, and it's also found in semiconductors. It conducts electricity and is what's used in microchips. And silicon has three isotopes, 28, 29, and 30, different masses. And the 29 isotope does not conduct electricity, while the 28 and 30 do. So if we can remove that 29 isotope, we get superconducting silicon, and we can make super fast semiconductors out of that. What does this mean in terms of how we make money? Well, if I take a bag of sand, a bag of normal silicon, that's perhaps $1 a kilo. But a kilo of silicon-28 is more like $600,000 a kilo. It's even more pronounced for carbon-14. A bag of charcoal, so a bag of carbon, a kilo of carbon is probably about $1 a kilo as well. But a kilogram of carbon-14 is $24 million. So we take these very normal elements, very normal chemicals, and we convert them to very special materials that have very specific properties that certain industries need. Now, the supply chain for isotopes has always been extremely challenged. This kind of chart explains why it's more challenged now than it has been in the past. But Russia is the largest producer of stable isotopes. And so the world is looking for a new producer of stable isotopes, and hopefully that's going to become us over the next several years. Now, we have two ways we enrich isotopes. The first is the aerodynamic separation process. The second is quantum enrichment. And ASP is essentially a bit like a centrifuge. When you think about a big traditional centrifuge that Russia or the UK uses to enrich uranium, it's a very large cylinder and it spins on its vertical axis. These plants are huge, the size of multiple football fields. They often have a power station next to them in order to supply them with energy to keep going. And they cost billions of dollars to build and take years to build. A new enrichment facility perhaps in a 5 to 10 year exercise. Our plants are much smaller and they're modular, and there's no moving parts other than the compressor. So we have a stationary tube, and we tangentially inject the gas into the tube, and we're able to accelerate it. And that way we're able to put it through various valves and flow directors, and that allows us to separate the heavy isotope from the light isotope. Our plants are much cheaper to build, tens of millions of dollars. And the time it takes to build these is about a year, that kind of time frame. And we're able to separate light isotopes as well as heavy isotopes. For a centrifuge to work, you need a lot of mass, heavy isotopes, something like uranium. whereas we actually prefer lighter gases, something like carbon-14 in the form of methane or silicon-28 in the form of silane. The downside to our technology is we use slightly more energy than a centrifuge, and that's one of the reasons why we're going to be moving starting to build plants in Iceland later this year, because the energy is so cheap there. It'll make us really competitive. Our second approach to enriching isotopes is quantum enrichment that uses lasers. Our second method is quantum enrichment, where which is great for something you can't turn into a gas, and so you vaporize a metal, pass it through a laser beam that's been specifically tuned to a particular isotope, and then we can excite or ionize one of the isotopes we've selected for and pick it out on a charge collector plate. Here are a couple of pictures of our plants. So this plant here is part of our carbon-14 plant, and you'll see here you have some separation units on the left-hand side, and in the middle you see the heavy element recovery. In the right you see the light element recovery. And these are places, our plants in South Africa. And most of this equipment is fabricated by ourselves. We have a construction team and a fabrication team that make a lot of this equipment themselves. This next slide here shows a picture of our laser laboratory and our laser plant. And this is our plant for ytterbium-176, which we completed construction of about 3 weeks ago, and is currently being commissioned at the moment. So to summarize, our plants are cost effective, they're modular, we can scale them as demand grows, and they're environmentally friendly. There's no nuclear waste, anything like that. So thinking about the opportunity in nuclear medicine, the first industry, it's one of the largest opportunities we have. The global medical isotope market is already very large, and it's growing substantially. Lots of new medicines and new diagnostics coming to the market, which need stable isotopes. This slide here just shows the symbiotic relationship between ASP Isotopes and PET Labs. PET Labs, our radioisotope company, produces or consumes a lot of stable isotopes and turns them into radioisotopes, while ASP Isotopes produces those stable isotopes. There's a real symbiotic relationship between the two, and we'd like to grow PET Labs around the world over the next several years, as it'll be the only back-integrated radiopharmacy that exists. So there are 3 medical isotopes of interest right now. The first is molybdenum-100, and we think that's an excellent alternative to molybdenum-99 that's currently the workhorse of nuclear medicine. Molybdenum-99 has a 66-hour half-life, so it halves in value every 2.5 days. It's a real troublesome product to ship around the world. And if you go back and look at earnings transcripts from Cardinal Health and Mallinckrodt back in the last decade or so, you'll see a number of profit warnings and problems getting those isotopes to where they need to be. Molybdenum-100 is stable. You can ship it in a FedEx package, and you can convert it into technetium-99 at the point of care. We think it's a much better way of producing technetium-99. Now, this is going to be a slow market for us to get into. These healthcare markets move more like glaciers rather than rivers. And so, this will be, we're looking forward to the next supply disruption in Moly-99. We'll be able to get a chance to start building more customers. This is our most exciting isotope in the short term, ytterbium-176. And Novartis have launched a new drug called Pluvicto, which is for prostate cancer. And it's a radioactive drug. It has an isotope called lutetium-177 in it, and that's what kills the tumor. And you make lutetium-177 from ytterbium-176. There's only one supply of ytterbium-176 today. That's Russia. And our plant's being commissioned at the moment. We hope to have commercial samples available this year, and start driving real revenues next year. That's the goal for ytterbium-176. Then zinc-68 is likely going to be our first plant in Iceland. And when you have a lutetium cancer drug, or a beta-emitting cancer drug, or an alpha-emitting cancer drug, like an actinium-based or lutetium-based radiotherapy, you need to have a gallium PET scan first. And gallium-68 comes from zinc-68. And so we're hoping to start building a zinc-68 plant in the next sort of few months in Iceland, and start producing zinc-68 next summer for this market. Here's a picture of part of our carbon-14 plant. And carbon-14 is used in the development of new drugs and agrochemicals. And we've signed a take-or-pay agreement, a multi-year take-or-pay agreement for carbon-14 with a Canadian customer. We expect to start enriching carbon-14 as soon as our feedstock arrives from Canada. We're expecting that to arrive in October. The plant is operational, it's working, it's currently enriching carbon-12 and carbon-13, and we're just waiting for our feedstock to arrive, and then this plant will start going. So just to summarize what I mentioned a moment ago about radioisotopes. So semiconductors is an emerging field that we think is very exciting. And I mentioned earlier, as you remove that 29 isotope, your silicon-28 becomes far more powerful in terms of the speed it can process information at and the rate at which it can process heat or dissipate heat at. And so we've got a lot of interest from many semiconductor companies, industrial gas companies who want enriched silicon-28. And so we've signed two small supply agreements, one with a US-based semiconductor company and the other with a large global industrial gas company to supply silicon-28. And we expect to start supplying silicon-28 before the end of this year. In addition to silicon-28, depleted germanium-73 is of interest to semiconductor companies. And we're in the process of talking to customers about who would like germanium-73, and we'd expect to start enriching that in our silicon plant next year. All of our plants today are in South Africa. Our plants use quite a lot of energy. South Africa is not known for cheap energy and reliable energy. As you saw a moment ago, we had a quick power cut. And so later this year, we're hoping to start building our first plant in Iceland. And we've secured a very long-term energy agreement in Iceland, sub 5 cents per kilowatt hour. And that would really drive down our cost of goods. And that'll allow us to really expand our gross margins and cut the price of some of these isotopes so they can be used in everyday electronics. So most investors are more excited about the nuclear energy opportunity than stable isotopes. The problem is fairly well known in that the world needs to double its electricity production between now and 2050 and keep net zero, to meet net zero targets. That's going to be a challenge. We think nuclear power, I think people agree that nuclear power is likely the best form of energy, green energy, to supply a base load to the grid. Solar is fantastic when there's sun. Wind is fantastic when there's wind, but it's not always sun and it's not always wind. Nuclear power allows you to have a base load forever. And 24 countries at the most recent COP meeting, COP28, agreed to triple the amount of nuclear energy by 2050. I personally don't think they'll manage it, but if they can double it, that's a huge move for the world. We think the future of nuclear energy is a small modular reactor. We think many others agree with us. Some of the companies involved in this industry, companies like TerraPower, Bill Gates was the founder and is the chairman of TerraPower. Oklo, Sam Altman is the chairman of Oklo. X-Energy, that's Cam Gafasian, and Rolls-Royce. And when you think about what made a motor car really cheap, it was the Ford Model T going onto production line. So production line economics, where you're producing over and over the same item. And SMRs are basically production line manufacturing for nuclear energy. So rather than building a 2, 3, 4 gigawatt nuclear power station in the middle of nowhere, having to build transmission lines to get that energy into the city or into local populations, these are much smaller. The clearance zone, the safety zone is maybe just a few hundred meters rather than a few miles, and they're much smaller in size. And they should allow us to give cheap energy to anyone in the world. The problem for these SMRs is they all require, a lot of them require a new form of uranium called HALEU, high-assay low-enriched uranium, and that's enriched to 19.75%. Traditional uranium used in nuclear reactors is enriched up to 5%, and so the energy density here is much greater. The problem is that there's no Western producer of HALEU today in commercial quantities. Centrus can produce a few small kilograms, but there's no real large producer of it. So we think our quantum enrichment technology is perfect for enriching uranium, enriching many other isotopes. And I've got to explain the science behind it earlier. This kind of contrasts and compares different types of enrichment. And you'll see the most important line here is the selectivity line, the alpha line. And so the selectivity for a centrifuge is about 1.15. And so that's good. And when you put those into a cascade, you compound that 1.15 across the cascade, and that gives you your desired enrichment. But for quantum leap or quantum enrichment, the selectivity is greater than 50. And here's an example of quantum enrichment in a real-world application. This is lithium-6 and lithium-7. So you'll see in the top chart there, That's lithium-6 is at 7%, and lithium-7 is at 93%. And after a single pass through our enrichment chamber, the lithium-6 is now over 90%. And so that's an enrichment factor of 112. So when we say greater than 50, we mean substantially greater than 50. Now, one of the problems a lot of SMR companies are facing right now is that nuclear fuel prices are moving quite a lot higher. The price of uranium ore is up sort of, 3-4-fold. Conversion price is up 4-fold. Enrichment price is up 3-fold. And this is really putting pressure on the cost of uranium for nuclear plants. When SMRs were being designed, the expectation was that HALEU would cost sort of $5,000 to $7,000 a kilogram. But actually now it's going to be more like sort of $20,000 plus per kilogram. And you'll see that cost is about half of it is the ore, about a third of it is the enrichment, and about a sixth of it is the conversion. Now, one of the things that makes us really excited about our technology is that because we've got a high enrichment factor, we believe we can take depleted tails. So this is nuclear waste sitting alongside previous, it's a waste out of an enrichment facility. We think we can take that nuclear waste and convert it into HALEU. And that will really drive down the cost of HALEU to a level where it can be used in any nuclear reactor really cheaply. And that'll hopefully drive nuclear adoption in the emerging markets where much more price sensitive to the cost of green energy. So we'll stop there and we'll start taking questions. But just to summarize, we have a proven proprietary technology that's been developed over the last 20 years. We've constructed 3 plants in South Africa, 2 using the ASP process and 1 using the quantum enrichment process. And there are multiple secular and geopolitical tailwinds that are helping drive customers towards asking us to produce isotopes. And so we're very, very optimistic about the next several years and the outlook for our business. So I'll stop there and take any questions, Anna.
All right, Paul, we do have some questions for you. Wayne says, you mentioned recently that ASP Isotopes is in approval discussions with 3 countries. So how many advanced nuclear power companies are you currently in partnership discussions with?
So how many advanced nuclear power companies? So we have signed 2 MOUs, both with large US-based SMR companies. Collectively, they need about $37 billion of HALEU between now and 2037. That's their goal. And we'll have to see how our discussions with governments go and if we can start building a facility somewhere. But the legislation and the legislative work and the licensing process is very complex and is not quick.
I can imagine. We have a question from Jeff. He wants you to describe the African plants being manufactured at each plant. Can you go into a little bit more detail with that?
So say it again, please. What I'm talking about.
Plants and the different types of isotopes currently being manufactured at each plant. That's the question Jeff has.
Right. Okay. So we have 3 plants in South Africa. The first is currently enriching carbon-12 and carbon-13, and we're waiting for our feedstock, which will come from Canada, hopefully in October. And that will allow us then to start enriching carbon-14. And carbon-14 is an extremely valuable isotope, let's say $24 million a kilo. And so that plant's operational, it's working, and it's good to go. The second ASP plant is a multi-isotope plant. It can produce a number of different isotopes. We're going to focus initially on silicon-28 because there's a real pull from the semiconductor industry right now to find a supply of silicon-28. Our process is quite unique in that we can actually enrich silane gas, and silane gas is actually what the semiconductor companies want to use in their fabs. Rosatom, large Russian nuclear energy company, they use a traditional centrifuge, and they have to enrich silicon tetrafluoride, much heavier form of silane that the semiconductor companies don't really want to use. And it's very difficult to purify that silicon tetrafluoride into silane with the purity you need to go into a fab. So it's a lot of excitement in the semiconductor industry about our products, and we hope to start producing product in that plant before the end of the year. We've got 2 customers waiting to receive it. And our third plant is our first quantum enrichment plant, our first laser plant, and that is in the process of being commissioned right now. And we will, we hope to start sending out commercial samples this year. And we're looking forward to that. It's great.
All right, Sebastian asks about the Iceland facility. Has it been permitted, and what timelines do you expect?
So we have most of the permits we need to start building the plant in Iceland. We're just waiting for one final permit to come through. We're expecting that fairly soon. Once we've got that permit, we'll start building it. And the goal is to have isotopes being produced in Iceland next summer. So that's the Northern Hemisphere summer. So August 2025, that kind of time frame potentially, maybe September 2025.
And capacity-wise, how much bigger is Iceland versus South Africa?
So Iceland, so our silicon plant, our multi-isotope plant, is about 4 times the size of our carbon-14 plant, and this plant in Iceland will probably be about 3 times the size, 4 times the size of that multi-isotope plant in South Africa, so substantially larger.
And roughly what percentage of Iceland will have been pre-sold or contracted?
We will not start building a plant there until we've contracted or pre-sold a sufficient quantity of product to guarantee generating a good return on the plant. So call that maybe 30 to 50% of the product we'd want contracted before we start building the plant.
And will Iceland mainly be Si-28 or zinc 67, 68?
So we're expecting Iceland to be things like zinc 68, silicon 28, xenon, germanium tetrafluoride, chlorine 37, nitrogen 15. So there's lots of isotopes we've got demand for, got interest in. And anything that is a gas, we can enrich for a gas, is likely to be done in Iceland.
And a question, I hope this makes sense, Paul. Do you see the ytterbium plant as a test case for QE to provide comfort to the market that the technology works? And if so, how's it going?
Absolutely. So this is our first quantum enrichment plant. Our scientists have spent a number of years developing it. And, if when we've got this plant successful and it's producing product, the plan is to start building other quantum enrichment plants. And so we have demand for nickel 64. We have demand for lithium 7 and lithium 6, and obviously there's a huge amount of demand for HALEU. And so, this really is the test case for quantum enrichment, and does what we do in our lab play out in the real world? And so far, things are looking pretty good. We've been commissioning it for 3 weeks now, and the laser system is up and running, and we're showing good signals there that it's correctly tuned into the exact wavelength we want. And so, a few more weeks to go, and hopefully we'll have some product out.
And Tim says, it looks like the recent equity raise went well, given the size and speed. So can you talk a little bit about that?
Yeah, so we were always going to think about IPOing Quantum Leap Energy as a separate business and spinning it out at the same time. And having spoken to bankers and now investors, the view was that doing an IPO concurrent with a spin out is a challenging thing to do. And actually, we'd be better off raising equity into our top company, ASPI, and dropping cash down into Quantum Leap Energy. So that's what we'll do. And, there's a lot of demand for the equity. We're well oversubscribed, and good long-term institutional US-based investors. So it's our first real US raise. So it was good to get that done. Our balance sheet's never been stronger, and so it's put us in a really great position to move forward now towards profitability and free cash flow generation.
And that's the next question. John asks if you're on track to get cash flow positive this year.
Yeah, we are at the moment. I mean, these plants have to come online, and there's a race against the clock within September. But certainly, things are looking pretty good right now. Hopefully we'll exit this year with cash flow positive.
Wonderful. Well, Paul, do you have any closing remarks for our viewers today?
Listen, thanks for your interest. Sorry about the interruption earlier. We often have power cuts here in South Africa. That's why the energy is so expensive. But thanks for your interest. It's an exciting time for ASP Isotopes. We've got a lot going on over the next sort of 3 to 6 months. And I look forward to giving you an update in a few months' time.
Wonderful. Thank you, Paul. We look forward to seeing you again soon.
Bye.
Okay, everyone, stay with us. We'll be right back.